The next question that we want to investigate is, given two sets of data, x, x1 through xn, and y, y1 through yn, how do we find that linear model, that linear relationship between x and y? So if x and y have an approximately linear relationship, then what we're going to say is that y is equal to beta 0 hat plus beta 1 hat times x. So we're thinking of beta 0 hat as being an estimator for the true intercept beta 0, and beta 1 hat as being an estimator for the true slope beta 1. And our goal is to figure out how to find that slope beta 1 hat and that y-intercept beta 0 hat. Now you'll recall that previously we looked at the height and weight data set, and essentially I just picked 2 points and computed the slope and the intercept. And I was able to do that because the means fell perfectly on a line. But you'll notice that our data is not necessarily going to fall perfectly on a line. You'll look at the CO2 concentration and global temperature example, and you'll notice that the data points are all scattered around that line that represents the mean. And we can't just pick 2 points and find the slope, because we could pick these 2 points, and that would give us a radically different slope than, say, these 2 points. Okay, we can't even pick the first and the last points in the data set, because those won't give you the best fit line either. So what we need is some sort of method for finding that best fit line. And that method is going to be the method of least squares. So our goal is to find that slope and that intercept that gives the best fit. But the question is how do we define best fit? The way that we're going to define best fit is it's a line that minimizes the sums of the squares of the error. What do I mean by the error? Well, the error is called the residual, or error, and that residual comes from estimating the data point y by the corresponding point on the best fit line. We'll call that yi hat, which is beta 0 hat plus beta 1 hat xi. So then the error is given by e sub I, which is y sub I, that's the data point, minus the point on the line. We'll call that y sub I hat. And below is a diagram that helps us see the residuals for the data points xi, yi. So for example, you'll see that x1, y1 lies above that line. The point on that line is going to be the point x1, y1 hat. And then the difference between the data point y sub 1 and y sub 1 hat is that red distance. We'll call that E1. And you can do that for all the data points. So you can see, say, xn, yn, and you'll have the point on the line that best estimates, which is xn, yn hat, and then the red line there would be en. And our goal is to minimize the sum of the squares of the red lines. And what we're really doing here by minimizing the sums of the squares of those red distances is we're minimizing variance. Because you can think about that the line here is the mean, okay? And the red lines are giving the variance, or the terms in the variance. So we're going to minimize variance. And that's how, essentially, by minimizing the sums of the squares of error, we're minimizing the variance, and that's how we're getting the best fit line. Okay, so to summarize, our goal is to minimize the sum of the squares of those residuals. that's going to be the sum from I equals 1 to n of y sub I minus y sub I hat squared. Now, if that was actually the variance, we would be dividing by something like n minus 1, but we don't need to do that in order to minimize that quantity. So we'll just define the sum of the squares of the errors to be the sum of the squares of these residuals. Now, how are we going to minimize the sum of the squares of the residuals? Well, you can see that the sum of the squares of the residuals is a function of the two parameters, the intercept and the slope. So it is the function, or it is a function of two variables. And so what we want to do is we want to minimize a function of two variables. And so how do we do that? Well, we have to go back to multivariable calculus. And we want to find the partial derivatives of this function. And we want to, of course, set those partial derivatives equal to 0. And that will give us a critical point. And so what we're going to do is look for critical points of this function. So the partial derivative that we want to look at first is going to be for the intercept. So that's going to be the derivative with respect to beta 0 hat of the sum of the squares of the errors, which is a function of beta 0 and beta 1. So we want to take the derivative of the sum from I equals 1 to n of y sub I minus, and I'm going to go ahead and put in what y sub I hat is. Y sub I hat is beta 0. Normally it would be plus beta 1x, but we're subtracting it, so it's minus beta 1 hat x sub I, and we're going to square that. So we want to take the derivative of that function. So the derivative of the sum is, of course, the sum of the derivatives. So I'll just take the derivative inside the sum. And to take the derivative, I've got the derivative of a big quantity squared, so that's 2 times that quantity. And then using the chain rule, I just need to take the derivative of the inside, and that derivative of the inside with respect to beta 0. So the only thing that depends on beta 0 is this term right here, and so the derivative of the inside is a minus 1. So the derivative actually isn't too bad. Okay, I'm going to take a 2, and I'm going to factor it out of the sum. And then I've got minus the sum of the y sub i's, because I've multiplied by minus 1. And then multiplying by minus 1, I've got plus, I'm going to write this as beta 0 hat times the sum of 1. So I'm factoring that out of the sum. I'm kind of distributing the sum here. And then I'm going to do plus beta 1 hat times the sum of the x sub i's. Okay, so the sum of the y sub i's, I can write that as minus n times the average of the y's, so y bar. Okay, so remember that y bar, I'll just write it over here, y bar is equal to 1 over n times the sum from I equals 1 to n of y sub I. And so what I'm doing is I'm multiplying by n, and then I'm solving for the sum of the y sub i's. So that's why the sum of the y sub i's there is ny bar. So I'm going to do something similar later, but beta 0, I'm going to sum from I equals 1 to n of 1. Of course, if you sum 1 n times, you'll get n. And then finally, beta 1 hat, the sum of the x sub i's, well, that's going to be n times x bar. I'm going to set that whole thing equal to 0 because I want to find where that derivative is equal to 0. Okay, So notice that I can go ahead and just divide out the 2. And then there's an n in every term, so I'm going to divide out the n. And so what I'm left with, if I solve for beta 0, is that beta 0 hat has to equal, bringing the y bar to the other side becomes a positive y bar minus beta 1 hat x bar. And so this derivative is equal to 0 when beta 0 is equal to y bar minus beta 1 x bar. What we're saying is that the mean of x and the mean of y lie on that best fit line, because we could rearrange this to say that y bar equals beta 0 hat plus beta 1 hat x bar. Okay, so that means that x bar, y bar, the mean of x, the mean of y, lies on the best fit line. Okay, so that gives us a sense of when that derivative is 0. But now we've got to look at the derivative for the slope, which is just a little bit more complicated. Okay, for the slope, we're going to want to take the derivative with respect to beta 1 hat of the sum of the squares of the error, which depends again on beta 0 hat and beta 1 hat, and we want to set that derivative equal to 0. So here we're going to have the derivative with respect to beta 1 hat of, again, the sum from I equals 1 to n of y sub I minus beta 0 hat minus beta 1 hat x sub I squared. Now, how we take the derivative for this one is very similar. So we're going to take the sum from I equals 1 to n of 2 times that quantity, y sub I minus beta 0 hat minus beta 1 hat x sub I. And then we want to take the derivative of the inside, but now the only term that depends on beta 1 is this one. And so we need to multiply by negative x sub I when we take the derivative with respect to beta 1 hat. So now I'm going to do something that's similar to what I did before. I'm going to take the 2 out, and then I want to distribute the sum. So this will be 2 times the sum from I equals 1 to n of x sub I, y sub I, and that has a negative sign on it, plus beta 0 hat times the sum from I equals 1 to n. I'm again multiplying in the x sub I. And then finally, beta 1 hat, sum from I equals 1 to n. And now x sub I times x sub I gives me an x sub I squared. Okay. So I want to see if I can simplify this. I want to find where both derivatives are equal to 0. So I'm going to substitute in for beta 0 here. Okay, so beta 0, as we saw previously, is going to be y bar minus beta 1 hat x bar. I'm going to substitute that in so that I get, let's see, 2 times the sum from I equals 1 to n of x sub I, y sub I. And then I'm going to get plus, I'm going to substitute in for beta 0. So that's going to be y bar minus beta 1 hat x bar. And then the sum of the x sub i's, that's an n x bar. And then plus beta 1 hat sum from I equals 1 to n x sub I squared. Okay. Let's do one more simplification here. So we're going to still get 2 times minus the sum from I equals 1 to n x sub I, y sub I, plus I'm going to get n x bar y bar when I multiply by that n x bar, and then minus beta 1 hat n x bar squared, and then plus beta 1 hat times the sum from I equals 1 to n x sub I squared. And then the goal here is to set that derivative equal to 0. So if I leave these terms on the left, that would be beta 1 hat times the sum from I equals 1 to n of x sub I squared minus n x bar squared. And then what I'm going to do is I'm going to take these terms, I'm going to move them over to the right. So that's going to be the sum from I equals 1 to n of x sub I, y sub I, minus n x bar, y bar. And of course, I can just divide out the 2. And so finally, I can solve for beta 1. So I'm actually going to move on to the next page and solve for beta 1. Well, I can actually solve for it right here. So let's see, beta 1 hat is going to equal the sum from I equals 1 to n of x sub I, y sub I, minus n x bar, y bar, divided by the sum from I equals 1 to n of x sub I squared minus n x bar squared. And that gives me beta 1. And it looks very complicated, but this is something that can be easily calculated using a computer, using something like a spreadsheet, right? We're looking at, in the numerator, the sum of all the x sub i's times the y sub i's, and then also the mean of x and the mean of y, all things that we can calculate using our data. And in the denominator, it's the sum of the x sub i's squared. We can calculate that using our data, minus n x bar squared. Again, x bar is something we can calculate with our data. So that can be calculated all using our data, and then beta 0 can be calculated once we have beta 1. It's just y bar minus beta 1 hat x bar. Again, those are all things that are calculated using our data. So at this point, we have what seems like a complicated formula for slope, but it's all in terms of our data. And the same thing for the intercept. It's all in terms of our data. But I want to try to get this in a slightly nicer form. So I'm going to do one more manipulation to get this into a nicer form. So I'm going to tell you that beta 1 hat can be written in this way. It can be written as the sum from I equals 1 to n of x sub I minus x bar times y sub I minus y bar. And the denominator can be written as the sum from I equals 1 to n of x sub I minus x bar squared. Okay, so we'll actually give these two things names. This will be capital S sub x y, and the denominator will be capital S sub x x. And so the denominator and the numerator, now look a little bit more like terms that we've seen before. In fact, that numerator is actually n minus 1 times, I'll use now a lowercase s of xy. Okay, that's supposed to be squared, actually. And that's supposed to be the sample covariance. And then the denominator, we could write that as being n minus 1 times s of x squared. And that would be the sample variance. So by writing things this way, we're really getting them in terms of two things that we can easily calculate on the computer, something like sample covariance and sample variance. But your book likes to use these terms, capital S sub xy and capital S sub xx. Now, why is it that this is equal to that? Why are these two things equal? So we want to finish off by making those computations. And in fact, I'm going to take the second one and make it look like the first one for you. So the first thing I want to look at is the sum from I equals 1 to n of x sub I minus x bar times y sub I minus y bar. And I want to see how I can rearrange that. So I'm going to multiply everything out. So that's I equals 1 to n of x sub I, y sub I, minus x bar, y sub I, minus y bar, x sub I, plus x bar, y bar. So I'm not going to do anything with that first term because it actually looks like what I want it to look like. But the next one I'm going to write as minus, I'm just going to distribute the sum, minus x bar sum from I equals 1 to n y sub I, minus y bar sum from I equals 1 to n xi, and then plus sum from I equals 1 to n x bar y bar. Okay, so everything in that sum was in parentheses, and so now I've distributed the sum. So what's going to happen here? So this will be the sum from I equals 1 to n of x sub I, y sub I, minus, so we have a sum of y sub i's, and we know that the sum of y sub i's we can write as ny bar. So what we really have in the second term is n x bar y bar. Then minus, we have the sum of x sub i's in the next term. That can be nx bar, so we have n x bar y bar. And then finally, we're summing up in the last term just constants. We're summing up the same constant n times, so that's going to be n x bar y bar. And so you'll see that the last two terms actually cancel, and that's exactly what we wanted for our numerator. Before we had the sum of x sub I, y sub I minus n bar x bar. So you can see it there, and now you can see it there. Okay, so the numerator works out, and it looks like the denominator is going to work out in pretty much the same way. So the sum from I equals 1 to n of x sub I minus x bar squared, we're going to write out what that sum is by expanding. So we're going to get x sub I squared minus 2x bar x sub I plus x bar squared. Then we're going to want to distribute the sum from I equals 1 to n x sub I squared minus 2x bar sum from I equals 1 to n x sub I plus sum from I equals 1 to n x bar squared. that first term is exactly what we want, so we're going to leave that one alone. We've got another sum of x sub I in the next term, so that's going to be minus 2 n x bar squared, because that sum becomes n x bar. And then finally, we're summing up a constant x bar squared, so that's n x bar squared. And so if we simplify this, we get the sum from I equals 1 to n of x sub I, and then minus n x bar squared. And that is exactly what we wanted in the denominator. Let's see if that's the case. Yes, that's what we wanted in the denominator. Okay, so that means we can rewrite what beta 1 is. Okay, so what we're going to do is now we're going to tell you what the slope is. Okay, so we're going to define s sub xy to be the sum from I equals 1 to n of x sub I minus x bar times y sub I minus y bar. And we're going to define s sub xx to be the sum from I equals 1 to n of x sub I minus x bar squared. And once we do that, we can then define the least squares line, or the regression line, which is the line that minimizes the residual sum of squares. Okay, that line is going to be beta 0 hat plus beta 1 hat times x. And beta 0, we said, was going to be y bar minus beta 1 hat x bar. And then the slope, beta 1 hat, is going to be s sub xy divided by s sub xx. And again, we want to recognize that s sub xy is really just n minus 1 times the sample covariance. And s sub xx is going to be n minus 1 times the sample variance, so that we can get it in terms of things that we can easily calculate using a spreadsheet or statistical software. So just to review what we've done, kind of let's go back and look at it. First, we defined what the sum of the squares of the errors were. And then we said, oh, we're going to take the partial derivatives and set them equal to 0 so that we can minimize that. And so I want to point out one last thing that I haven't talked about yet, and that is that why is it that the critical point is a minimum and not say a maximum, or neither? Okay, and this is something that you can show using second derivatives, but I just want you to see that the sum of the squares of the error that we're looking at, right, this function is always going to be positive. And since that function is always going to be positive, if I find a critical point for that function, then that critical point has to be a minimum.